Part 2 of points of inflection looks at a slightly more complex curve, and typically what you're asked to do is consider the curve, find the stationary points and their nature. Sometimes you're asked to find the point of inflection, in this case you would be, and then you're asked to sketch the graph. So these things take a bit of work, okay, and they're going to take a page of work by the time you've done your graph. But it's not difficult if you just follow carefully what's going on. Okay, so first derivative, now a careful expansion using both the product and the chain rule. Derive the first, which is 1, multiply it by the second, plus derive the second, now there's the derivative of the second, multiply it by the first. Okay, I'm going to factorise and get to this point here. And I need to get to this point here because I'm going to solve next for stationary points. And again, I'm showing you the communication you need with the examiners. If you've got to solve something, it's no good having this sort of thing. You can't solve that to 0. You need a product, something times something. Okay, so we have this thing equals 0, so either that bracket equals 0 or that bracket equals 0, and we get the solution of -1 and 2. Remember again, I've suggested that you write the two solutions in order, numerical order, so it just gives you a plan for your graph. Straight away, substitute -1 back into the equation to get your y coordinate, and there they are there. Okay, we're going to use the second derivative, and the second derivative again is a product rule and a chain rule, so again there's a fair bit of work. Now, what I've done is I've actually expanded and simplified that expression because I have to solve this for 0, and again it's no good having all this thing here equals 0. So I've taken a bit of a shortcut with the algebra. You can look at that in your own time. We're going to use this now to test for points of inflection. I'll begin by testing, first of all, the nature of the stationary points and then the point of inflection. Now, this is an interesting one. When x equals 1, the second derivative is equal to 0. Now, when you've got a second derivative, you're expecting it to be positive, which is concave up, negative, which is concave down. This one is 0, which means it is not a turning point. Okay, now we'll come back to this in a second, but if it's neither positive nor negative, it is not a turning point. It's a stationary point, not a turning point. There's the test at x equals 2, y double dash equals 36, so it's a minimum turning point. And this expression, or this description again, is important in terms of your working. For a point of inflection, we want the second derivative equal to 0, and you can look at that. We get two answers, positive and -1. Again, find your y coordinates straight away. Now, here's the important thing. We've got to test both points of inflection. So there's -1, +1. Choose numbers either side of those, and we get positive, negative, positive. And therefore, this thing looks like there's 2 points of inflection. So let's have a look at the graph. So we've got no turning point here. We do have a turning point here. And I suppose, look, I'll make this link while we're on the job. Up here, okay, I have a stationary point of -1. And down here, I found a point of inflection of -1. So those two things coexist. So it's not a turning point, but it is a point of inflection. So think about how you might graph that. And what I'd like you to do is stop the video now, attempt a sketch of this question, and then move on and look at the graph because I'm about to show you. Yeah, I said before you go on with the video, try and sketch the graph. So do that before you watch the next slide. Okay? Very good. So here we are with our sketch. Okay, now we found 2 points of inflection and 1 turning point. But we did find that this thing here is a stationary point, but not a turning point. The concavity was positive, so concave up here, but concave down here. So it's a stationary point. That means it's not a turning point, but does stop. The gradient stops there, then continues down. So we have gradient of negative there and also negative there. gradient has not changed. It's come to rest at 0, but concave down, up, concave down. There's our point of inflection. So this part of the curve here, okay, this part here is concave down, but not including 1, negative 1, and not including 1. They're points of inflection, so they are neither concave up or concave down. And finally, you can see that everything from 1 upwards is concave up, and there's our turning point down there. So that's how you interpret the information. Finally, you might be asked things like, well, where is the curve decreasing and concave up? Well, if it's decreasing, that means it's coming downwards. And where is it concave up? Well, it's concave up here, so everything is less than negative 1. It's concave up, but decreasing, falling down. Here's our other point of inflection, so it's also decreasing between 1 and 2, and it's also concave up. So we've got those two situations there and there, where you've got a decreasing curve, the first derivative is negative, and concave up, the second derivative is negative. So there you go, there's the second of our 3 examples for points of inflection.